Alrighty. So then we're going to get started with our lesson today. Today we are starting chapter 9. We completed chapter 8 last week with section 8.3 about estimating population means. And now we're continuing and moving on to the next part, which is testing a claim. And this kind of jumps off from the estimating part. Right, chapter 6, 7, 8, 9, they're all very closely related. We're building on these concepts. And so that's where we're headed today. If you have not completed the assessments for chapters 6, 7, and 8 yet, it's okay, you still have time. Please keep in mind that at some point I do put in placeholder grades that may harm your current grade, right? I mean, chapter 6 has placeholder grades if you haven't submitted it yet. Chapter 7 will probably be happening later this week. Chapter 8 probably not until after spring break. But remember, once you submit your assignment, it gets graded. There's no penalty. Your grade will be updated. So please keep that in mind. But again, you don't want to let this build up too much because that could cause problems later. So think about those things. And if you need help, please ask. I'm more than happy and willing to give you help and support either through email, messages, send you pictures of ideas. You can send me a picture of work that you've done to ask if you're doing it correctly or not. I'm totally happy helping you in that way. But you have to reach out and let me know you need help. All right. So with that, we're going to move on to chapter 9. We're going to do a presentation here. I've got some examples for us to look at the end of the presentation, which we may or may not get through all the examples, but if we don't, we'll finish them up tomorrow when we do our activity. So here we go. Let me share my screen. That one. Alrighty, so here we are, chapter 9, testing a claim. Section 9.1 is significance tests, just the basics. We will discuss the particulars for significance testing with proportions and means in section 9.2 and 9.3. But for now, we're just getting the concept and idea. For this lesson today, our objective is to be able to state the null and alternative hypotheses for a significance test about a population parameter. And remember, we're using parameter now because we're not differentiating between proportion and mean. At this point, we're just looking at the overall concept. We need to be able to interpret a p-value in context. We want to be able to determine whether the results of a study are statistically significant and make an appropriate conclusion using a significance level. Okay, sorry, a student just messaged me about something and I'm wondering why they're not in class. We'll deal with that later. So, continuing on, we need to be able to interpret a type 1 and type 2 error in context and give a consequence of each. So those are our goals for today. So here's our introduction, right? Confidence intervals are one of the two most common types of statistical inference. We use a confidence interval when your goal is to estimate a population parameter. So we'll use that type of inference when we want to estimate a proportion or a mean. All right. The second common type of inference, called significance tests, has a different goal. Right, to assess the evidence provided by data about some claim concerning a population. Right, so confidence intervals are used to make an inference about what a parameter might be, estimate a parameter. Significance tests helps us evaluate or make an inference about a claim. A significance test is a formal procedure for comparing observed data with a claim, also called a hypothesis, whose truth we want to assess. The claim is a statement about a parameter, like the population proportion P or the population mean mu. We express the results of a significance test in terms of a probability that measures how well the data and the claim agree. So this is the idea of a significance test. We're evaluating a claim. So we're going to run this little simulation here. And the way it'll work is we'll have this little screen here. It won't look like this one. It'll look similar, right? And we want to assess a basketball player's claim that he makes 80% of the free throws he attempts. We think he might be exaggerating. To test this claim, we'll ask him to shoot some free throws virtually using our simulator, using the reasoning of a statistical test applet at the book's website, right, which I have pulled up here. I'll launch it in a moment. So we'll launch the applet. We'll set the applet to take 25 shots, click shoot, record how many of the 25 shots the player makes. All right, we'll do it again for 25 more shots. We're going to repeat until we are convinced either that the player makes less than 80% of his shots or that the player's claim is true. And then once we've decided what we think is right, we're going to click show true probability and see if we were correct. So that's how this thing's going to play out. So I need my test. And I need to reset. All right. So here's our little simulator here. We're going to do 25 shots. And we're going to ask our simulated basketball player to take some shots. So they're going to shoot 25 shots. And we can see it didn't start out so great. Missed a bunch. Right. And as we get to the end of the first 25 shots, we are not looking so great for him. All right. He hit 11, missed 14. So his rate is actually at 44% for this set of 25. All right. So then, all right, that's only 25 shots. Let's have him do some more. So we'll run our simulation again. 25 more shots. And we're still pretty low. All right, let's go one more round of 25 shots just to see what happens. Maybe he can go on a streak here, right? Oof. Okay. So here we are. Based on our simulation, he's taken 75 shots. He's made 35, missed 40. Do we think this basketball player's claim is true? What do you guys think? Based on our simulation here, do we have evidence to support his claim? Or do we have pretty good evidence to say he's probably exaggerating? What do we think? Yeah, it's not looking so good for his claim, right? So let's see, what's our true probability here? All right, so this green line, it might be a little hard to see, as our true probability looks about 45%. So this guy is definitely over-exaggerating, or at least we have evidence to say that he's over-exaggerating. You know, maybe if it goes longer, it'll move its way back up, but for now, Not looking so good. All right. So let's go back. All right. So this is just kind of our intro here. So a significance test starts with a careful statement of the claims we want to compare. The claim we weigh evidence against in a statistical test is called the null hypothesis. We notate that as H sub 0, or say H naught. Often the null hypothesis is a statement of no difference. Right? H 0, 0 is no, nothing, right? The claim about the population that we are trying to find evidence for is the alternative hypothesis, H sub A for alternative. In the free throw shooter example, our hypotheses are H naught, colon, parameter P equals 0.80, 80%. Our alternative hypothesis, H sub A, P is less than 0.80, where P is the long run proportion of made free throws. All right. And so we got a few things going on here that I want to take note of. We're using the parameter P. We're not using P hat. Right? This is talking about a parameter. Our null hypothesis is equal to what the basketball player's claim is, so to say. And then the alternative is what we're trying to find evidence for. We think he's over-exaggerating. Right? And we're also clearly identifying what P represents. P is the long-run proportion of made free throws. That's all needed when stating your hypothesis. You need to be very clear and specific. Right? If you need a moment to write anything down, can you please raise your hand? All right. In any significance test, the null hypothesis has the form H naught parameter equals value. It is equal to our value. The alternative hypothesis has one of the forms, H sub A parameter less than value, H sub A colon parameter greater than the value. This should be the same value as we have up here. And H sub A colon parameter not equal to the value. So it can be less than, it can be greater than, or we might just be interested to say that it's just not that value. Could be greater than or less than. To determine the correct form of H sub A, or alternative hypothesis, we want to read the problem carefully. The alternative hypothesis is one-sided if it states that a parameter is larger than the null hypothesis value, or if it states that the parameter is smaller than the null value. Right? One-sided. So these first two, H sub A parameter less than, parameter greater than, those are one-sided. It is two-sided if it states that the parameter is different from the null hypothesis value. It could be either larger or smaller. That's the last option here, parameter not equal to value. That is two-sided. If you need a moment to write some of this down, please raise your hand. Our hypothesis should express the hopes or suspicions we have before we see the data. It is cheating to look at the data first and then frame hypotheses to fit what the data show. It's not fair. Hypotheses always refer to a population, not a sample. Be sure to state H naught and H sub A in terms of population parameters, P, mu, sigma, right? It is never correct to write a hypothesis about a sample statistic such as P hat or X bar. Right? These are very important things to note. We want to make sure that we don't make these errors. Again, if you would like a moment to write some of this down for your notes, raise your hand. Okay. So suppose a basketball player claimed to be an 80% free throw shooter. To test this claim, we have him attempt 50 free throws. He makes 32. His sample proportion of made shots is 32 out of 50, or 0.64. What can we conclude about the claim based on this sample data? Right. Well, we could use software to simulate 400 sets of 50 shots, assuming that the player is really an 80% shooter. Right, so we assume the null hypothesis is true. Right, we run this software and simulate 400 sets of 50 shots. You can say how strong the evidence against the player's claim is by giving the probability that he would make as few as 32 out of 50 free throws if he really makes 80% in the long run. We can see based on this simulated data, in 400 sets of 50 shots, there were only 3 times when our shooter made as few as the observed p hat equaling 0.64. Which essentially is kind of like, well, if he really is an 80% free throw shooter, how did this happen? Based on the simulation, our estimate of this probability is 3 out of 400, or 0.0075, right? Less than 1%. The observed statistic is so unlikely if the actual parameter value is p equal 0.8 that it gives convincing evidence that the player's claim is not true. There are 2 possible explanations for the fact that he made only 64% of his free throws. These are not answers, these are just ways that we could reason how this happened. There's 2 options. 1, the null hypothesis is actually correct. That's one possibility. And the player's claim is correct, and just by chance, a very unlikely outcome occurred. The other explanation is the alternative hypothesis is correct, meaning his proportion is actually less than 0.8, so the sample result is not an unlikely outcome. Those are the 2 possibilities of this data. Either he just by chance had a very unlikely outcome, or he is, exaggerating his free throw percentage, and the alternative hypothesis is correct, and his proportion is actually less. And this result is not unlikely at all. In a nutshell, an outcome that would rarely happen, such as the one we just saw, if the null hypothesis were true, is good evidence that the null hypothesis is not true. Notice how this is worded. We're not saying that the alternative hypothesis is correct or that the null hypothesis is definitely wrong. We're saying we have evidence that it could maybe not be true. Right. Is there anything I can clarify about these statements? Does anyone need a moment to write anything down? Please raise your hand. So the null hypothesis H naught states the claim that we are seeking evidence against, right? Essentially, we're seeking evidence against the free throw percentage of 80%. The probability that measures the strength of the evidence against a null hypothesis is called a p-value. The probability, computed assuming H naught is true, which is how we calculated that 3 out of 400 for our basketball shooter, that the statistic would take a value as extreme as or more extreme than the one actually observed is called the p-value of the test. Small p-values are evidence against H naught because they say that the observed result is unlikely to occur when H naught is true. Large p-values fail to give convincing evidence against H naught because they say that the observed result is likely to occur by chance when H naught is true. Right, so if something's still relatively likely to occur, then it's not evidence against the null hypothesis. It's saying, well, if the null hypothesis is true, this is still something that could happen. It's not unreasonable. Small p-values are evidence against the null hypothesis, because it's saying, well, if this thing is true, the outcome we saw probably shouldn't have happened. It's very unlikely to happen just by chance. So it's evidence against that hypothesis. Right. See, we need a moment to write anything down. Please raise your hand. Is there anything I can clarify so far? The final step in performing a significance test is to draw a conclusion about the competing claims you are testing. We make one of two decisions based on the strength of the evidence against the null hypothesis and in favor of the alternative hypothesis. We can reject the null hypothesis or fail to reject the null hypothesis. Those are the choices. Note: a fail to reject H naught decision in a significance test does not mean that H naught is true. For that reason, you should never accept H naught or use language implying that you believe H naught is true. It's simply we don't have enough evidence to say that it's not true. So we're going to fail to reject. In a nutshell, our conclusion in a significance test comes down to: if the p-value is small, then we reject H naught, and we then have convincing evidence for HA, the alternative. If the p-value is large, then we fail to reject H naught, and we do not have convincing evidence for the alternative. Okay. I would recommend writing this idea down. It gives us language that we can use: reject H naught, fail to reject, convincing evidence. This is how we need to write our conclusions. We need that verbiage. And we'll next see how we decide what is small and large for a p-value. So we need a moment to write anything down. Please raise your hand. So, statistical significance. There is no rule for how small a p-value we should require in order to reject H naught, but we can compare the p-value with a fixed value that we regard as decisive, called the significance level. We write it as alpha, the Greek letter alpha. It's kind of like the Greek letter A. Right. If the p-value is smaller than alpha, we say that the data are statistically significant at level alpha. In that case, we reject the null hypothesis H naught and conclude that there is convincing evidence in favor of the alternative hypothesis HA. So again, When we use a fixed level of significance to draw a conclusion in a significance test, right, the p-value is small, less than alpha, then we reject H0 and we have convincing evidence for HA. When the p-value is large, greater than or equal to alpha, we fail to reject H0 and we do not have convincing evidence for the alternative. Right, so our significance level, alpha, gives us that kind of cutoff mark to say if this thing is small or large, which is incredibly helpful when trying to decide, how do we make our conclusion? If we need a moment to write this down, please raise your hand. Okay. Now that we can make a conclusion, there's things that we can mess up. We have type 1 and type 2 errors. When we draw a conclusion from a significance test, we hope our conclusion will be correct, but sometimes it will be wrong. There are two types of mistakes we can make. If we reject H0 when H0 is true, we have committed a type 1 error. If we fail to reject H0 when HA is true, we have committed a type 2 error. It's a little easier to see with this table here, right? So we have the truth about the population, either H0 is true or H0 is false and HA is true, and the conclusion that we made based on our sample. If we reject H0 when H0 is actually true, we have a type 1 error. If we reject H0 when H0 is false and HA is true, that's good. We were correct. If we fail to reject H0 when H0 is true, excellent, that is correct. If we fail to reject H0 when H0 is false and HA is true, that's a type 2 error. Okay. So we need a moment to write this down. When dealing with type 1 and type 2 errors, we can determine the probability of a type 1 error because it's the probability of rejecting H0 when it is really true, and this is exactly the significance level of the test. Right, the significance level alpha of any fixed level test is the probability of a type 1 error. That is, alpha is the probability that the test will reject the null hypothesis H0 when H0 is actually true. Consider the consequences of a type 1 error before choosing a significance level. And we'll deal with what consequences could be in a later example. Right. And there are ways to determine the probability of a type 2 error, but that comes later. Now we're just dealing with type 1. See, we need a moment to write anything down. So then we're going to look at some examples of how to apply what we just saw. In our first example here, we have hemoglobin. Well, our first example and the second example, we want to state an appropriate null and alternative hypothesis. That's kind of the first step, right? We need to be able to identify the claims and what we're trying to show. So hemoglobin is a protein in red blood cells that carries oxygen from the lungs to body tissues. People with less than 12 grams of hemoglobin per deciliter of blood, grams per DL, are anemic. A public health official in Jordan suspects that Jordanian children are at risk of anemia. He measures a random sample of 50 children. Right, so we have this 12 grams of of hemoglobin. That's kind of like our value, right? So then we need to have our H naught, right? What's our null hypothesis? And our alternative, H sub A. We're dealing with values and not percentages, right? And in this case, we're looking at averages, right? We're not specifically, it doesn't say the average, but we're dealing with, okay, if we sample a whole set of people, right? And we want to know how many grams of hemoglobin per deciliter of blood they have, we're going to deal with an average. So we have the mu, right, mean, being 12 grams per deciliter, would be our null hypothesis, right? It's the no change hypothesis. It will be equal to this thing. The less than part, right, that then becomes the one-sided hypothesis here for the alternative. All right, so our alternative hypothesis is that the mean will be less than 12, right? Because that's really what we're interested in. We want to know, because if the alternative is true, that means the children are at risk. Right? And the last thing we need to say here is we need to identify what is mu. Right? So we can write where mu is the true mean amount of hemoglobin in Jordanian children. We need that last statement stating what mu is. Otherwise, we've just provided a variable that's not been identified. That's a big no-no. Is there any questions about how I came up with the null and alternative hypothesis for this scenario? Okay. Let's look at another example. Right? Simon reads a newspaper report claiming that 12% of all adults in the US are left-handed. He wonders if the proportion of lefties at his large community college is really 12%. Simon chooses an SRS of 100 students and records whether each student is right or left-handed. Right. We have a percentage here, so now we're dealing with proportions. So our parameter will be P. Right. Our null hypothesis will be that P equals 12%. The alternative, given our context here, Simon doesn't care if it's more than 12% or less than 12% specifically. We didn't see that written there. So we're just saying that it's not 12%. Could be more, could be less. So we have P not equal 12%. And then again, clearly identify what P is. So is there anything I can clarify about this example? So then let's consider the Jordanian kids example again, and we want to explain and interpret some stuff. So for the study of Jordanian children, the sample mean, right, which would be X bar, hemoglobin level was 11.3 grams per deciliter, and the sample standard deviation, right, S sub X, was 1.6 grams per deciliter. The significance test yields a p-value, right, of 0.0016. Part A here, explain what it would mean for the null hypothesis to be true in this setting. We're not considering the results. We just want to know, what does it mean if the null hypothesis is true? Right. So in this setting, that would mean that Jordanian children are not at risk of anemia. On average. And that's because if the null hypothesis is true, then their hemoglobin level is not less than 12, because it's equal to 12. So we're good, right? They're not at risk. Part B, interpret the p-value in context. So again, I'm not at the stage where I'm writing a conclusion about what this means. I'm just stating, what does the p-value mean in context? Right? And so the p-value means, like, if we assume, right, that the null hypothesis is true, right, the hemoglobin level is 12, there is a 0.0016 probability of getting a sample mean of 11.3 or smaller just by chance. In our sample. And that's what our p-value means in this context. Right? There's a very small chance of getting that value just by chance, if our null hypothesis is true. Is there anything I can clarify about this part of this example? So then part C here, now we're being asked to make a conclusion based on a significance level and the p-value we have and the results of our sample. Right, what conclusion would you make if alpha, our significance level, equals 0.05? Right, if alpha was 0.01, we need to justify our answer. All right, I'm going to boil this down to a single statement here for both scenarios. Right, in both cases, don't know this thing keeps glitching this way. Right. The p-value of 0.0016 is less than alpha. So we reject the null hypothesis. We have convincing evidence that the true mean hemoglobin in Jordanian children is less than, this thing's just freaking out, 12 grams per deciliter. So based on the results, based on our p-value and the provided alpha levels or significance levels of alpha, right, we can make this conclusion. Right. So again, is there anything I can clarify for this example? You guys understand how we get to this point where we get to reject the null hypothesis? Okay. All right. There's another example that we can work through, but we're going to do that to start class tomorrow before we do our activity to help us understand this section a little bit better. So that is the end of today's presentation and the lesson and examples. If you have any questions, comments, concerns about the lesson or anything else we covered today, please feel free to stick around and talk to me, let me know. Otherwise, you could message me, send me an email, what have you. And other than that, enjoy the rest of your day, and I will see you all tomorrow.